at least for this, you want to do a full analysis. So maybe not just look at polarity or not just look at base, conjugate base, but the whole overall factors for this. And so just a couple of things. I mean, when we look at acetic acid, there are different ways I look at the polarity here. Okay, so the first way I look at the polarity is by looking at the oxidation state of the carbon that's attached to the alcohol here. And so we're looking at plucking this proton off. These protons are not very acidic. Why? Well, if you're in a base, like hydroxide, you're going to be attracted to hydroxide. What's the charge on hydroxide? Minus. So you're going to be attracted to positive. Well, these aren't very positive, so you'll be attracted to this one. This one should be quite a bit more positive. And so one of the things I look at is what is the oxidation state of this. So this is inductive effect that we're talking about. And so this is one way of looking at the inductive effect. One way of looking at the inductive effect is to consider this carbon here. So let me redraw this. And so what is the oxidation state of this carbon here? Not zero. Not minus 3.
Minus 1.
Not minus 1.
Plus 2.
Oh boy, it's been a while since oxidation states.
Oh, oxidation.
Let's start off. What is the oxidation state of this hydrogen? 0. When are you going to review this? The night before the test? Yeah, that used to be me. Used to be me. I have to have so much stuff to review. Just completely overwhelmed. Yeah. Formal charge is 0, so that's good. You've gotten the formal charge. Great. Great. Yeah. But oxidation state is a little bit different. Oxidation state is assuming the bond is 100% ionic or 100% covalent. Yeah, 100% ionic, which means the winner take all. And who's the winner in this case? Carbon plus 1. What's the oxidation state of this carbon? Okay, it's 2, 4, 6. It takes all the electrons from hydrogen and then half of this because this is a tie. So 7 minus 3. Is that electron rich or electron poor or just happy as is? Electron rich. Then we go to this carbon. What's the oxidation state on this carbon? Plus 3. So we got a minus 3, which is pretty rich, attached to a plus 3, which is pretty, what? Poor. So this is pretty poor. Okay, what about this carbon here? Ethanol. I'll just show Ben. Minus 3 for the carbon on the left, I think. It's pretty rich. How about this one?
Plus 1.
Minus 2 takes 2 electrons from hydrogen and gets taken to 1. Now that is in minus 1.
Okay, 2, 4, none of these, half of these. 2, 4, 5,
Minus 1.
minus 1. Is that rich? On the rich end or the poor end?
It's on the rich end.
It's on the rich end.
It's mostly mild.
Then you combine it with this. Okay, so this is by oxidation state. Induction effect by oxidation state. This is what we call an electron withdrawing group that's attached to the R. So ROH. This first one is electron withdrawing. Do you see how it's going to suck electron density away from the alcohol, or the OH, the hydroxyl? I should call this hydroxyl because the whole thing is called a carboxyl group. We don't call this an alcohol, we call it a carboxylic acid. Do you see how this thing that's attached to the OH, the hydroxyl, is electron withdrawing? Yeah. Over here, the ROH is quite a bit different. This R is an electron, not withdrawing, it's an electron rich group, which is what we call an electron pushing group. And so we have an electron withdrawer and an electron pusher.
Kind of a mild question. Why is it called an electron pusher?
It's electron rich. It's got plenty of electron rich density to share.
So it pushes the electron away?
You can come up with another name. What's your name?
Electron depositor.
Electron.
You have electron withdrawer and electron depositor. Think of it
Well,
like a bank.
Electron positive, you get people confused. Because what is the charge on electrons? And people will go, positive electron, that must be a positron. So I don't know. I don't really think electron positive would be good.
I'm just genuinely curious what's the name. Because when I think of withdraw, I think of pushing.
Well,
I can see the difference.
maybe I shouldn't, call it electron push. Sounds like a drug dealer or something. Electron pusher.
How about donation?
Electron donor? Well, it's not really a donor because a donor would be like a Lewis. We use the term donor for Lewis what? Yeah, so we don't want to get it mixed up with that. Unfortunately, they did that here. I don't think this is good. They call it electron donor and withdrawer. Withdrawer is fine. Here. Maybe I better narrow the scope. Organic. Well, I don't know who came up with the name. That's just a name I learned. So I'm going to give myself electron pushing in organic chemistry. This is a big topic in organic chemistry. You have electron pusher substituents and you have electron withdrawal substituents. These are organic chemicals here, so we'll just use the organic chemistry jargon. Why do we pick pushing? I don't know why they pick pushing. But if you can tolerate it, that's what we'll use. Electron pushing. So we have electron pushing groups and we have electron withdrawing groups. And so let's look at the electron withdrawers. What are electron withdrawing groups in organic chemistry? But he has donating. I don't like donating. EWG, electron withdrawing group. So that would be our EWG here. But on the right, it's not an EWG. I don't know. If we use pushing, it should be EPG, but
If we use donating, it's
this is from UCLA. Let's see what UCLA uses. So UCLA has electron withdrawing group. EWG. Let me check their,
Oh, I see it. Electron releasing group
oh, their
with ERG.
electron donating group, electron releasing group. Okay, so they use electron donating and electron releasing. I don't like donating because it mixes up Lewis. This is not Lewis. This is for substituent. So I learned it as pusher. So, but you could call it electron, and I don't like releasing because then it sounds like redox. So I'll just continue using pushing. So the inductive effect is going to be stronger in which one?
The electron withdrawing group.
Yeah, electron withdrawing is going to suck electron density from this. This is electron pushing group.
Mr. Trudell,
Yeah.
is pushing and withdrawing relative to each other?
Yeah, one, they're opposite.
Like if there would be something that's even more of a pusher, then that would be called like withdrawal. But if something had a more inductive effect than that
It would be a greater withdrawal.
greater withdrawal, would that still be considered withdrawal though? Would that
Withdrawal are, basically it's this. Withdrawal are electron pore groups. Any kind of electron pore groups you attach are going to be withdrawals. And pushers are all going to be electron rich groups. So this is why we're looking at the oxidation states. Not that many. This is the way I usually do it. When I think of the inductive effect, I usually go to oxidation states because it's just convenient. That's the most common way, though, and this is the way everybody learns, is by terminal electron pore species. And so, if we compare like this, so electron pore species would have high electronegativity. And so we say terminal electronegative atoms, like oxygen here. And that's going to just set up a chain. This is the induction effect. So we always go to the terminal like this. Carbon versus oxygen, even though oxygen should win here, it's different here. For this carbon oxygen is still win. However, this carbon losing electron density to this oxygen makes it more electronegative. And therefore, this carbon is going to put up a greater fight against this oxygen. So this is kind of the reverse direction of what we expect. We expect the arrow to be pointed towards oxygen, as I mentioned before, because oxygen is more electronegative. But because this terminal electronegative group bonded here, it kind of makes it less so. And so this is just showing it making it less so. Yeah. And so we're going to have a larger delta plus. Whereas for ethanol, and some people wrote this on their thing. We don't have the same effect. This is called the inductive effect when you have a chain of these dipoles. This is just bond polarity here for a mild inductive effect. Just one single. Here, this is going to be pointed in the correct direction. Carbon versus oxygen. Oxygen is going to win. This is carbon's electron rich, right? The oxygen wants to take those electrons. This is going to result in smaller particles. So in terms of polarity, which one is greater? Acetic acid. Well, number one and number two are just showing two different ways of showing the inductive effect.
For acetic acid.
Yeah.
Yeah, acetic acid would be popular.
Either of these ways is fine. I'm just showing you two different ways to do it. Okay, so in terms of polarity, acetic acid is going to be more polar, which is going to attract bases more. And so if you're a base like hydroxide, which hydrogen are you going to be most attracted to? Yeah, this one. So this is the one that gets attacked first. And then which one would be, let's say I had a mixture of ethanol and acetic acid. So the first hydrogen to be attacked would be this. And once you run out of this hydrogen, the next hydrogen that you may attack would be on the ethanol. You think once you run out of this, then you have ethanol. So ethanol, well, this is the next best. And so we should do that. The bond strengths are about the same. The bond polarities are a little different because we're looking at the inductive effect. The inductive effect is what is that attached to? If we only look at the bond itself, the OH bond, the delta EN for that is already fixed. So we have to look deeper, and we'll continue to look deeper. Because the bond polarity actually turns out to be different because of the inductive effect. But you might think, okay, once we run out of acetic acid, then this should react as an acid, but it's still not a very good acid. You know, our next best acid is still not very good, but if it's the best around, then with it. And so ethanol is not normally considered an acid. The reason is because, and a lot of people didn't do this, we also have to look at the, what's another factor that's going to influence?
The stability of particles.
Yeah, the stability of the conjugate base. You have to clearly state, I mean, some people were stating the base, but they didn't show the base. You got to show the base. And you don't confuse the two. You can't say acetic acid base strength. Acetic acid is not a base. Acetic acid is an acid. It could be a potential Lewis base, but it's not a. So when we're talking about base, we're talking about the conjugate base. And so make sure you say the conjugate base if you don't drop, Which a lot of people didn't, they just said the base, acetic acid. No, that's not right. And then for the stability, what we like to do is, for acetate, which would be the conjugate base here, we're going to have how many resonance structures?
2.
We're going to have 2 resonance structures. And so you could say, and a lot of people said this, there are 2 resonance structures here. But you don't want to leave it at just 2 resonance structures because that's not detailed enough. So you have to mention about those 2 resonance structures where we can, but what's most important in base strength?
The more resonance forms,
The more resonance forms, the more stable. Now, why? You can't say 2 resonance forms because it's more stable. You have to say why 2 resonance forms would be more stable than having 1 or none.
because the negative charge is more dispersed.
The negative charge is more dispersed. So we say it's more delocalized. And so that's fine. And so some people do the hybrid, which is good. But the hybrid, let's notice some people made a mistake with the hybrid. With the hybrid, what happens to the pi bonding electrons? They spread out. Remember, this is sp2, sp2, sp2. The p orbitals are all perpendicular to the page, so they're going to spread out over the p overlap here. And so to show that the pi bonding electrons are spread out over these 3 overlapping p orbitals, the p orbitals are going to look like this. There's one lobe sticking out, there's another lobe sticking in. One lobe sticking out, one lobe sticking in. So these p orbitals overlap like this, and therefore the pi bonding electrons are spread out over those 3 p orbitals. Do you see that? What that's going to do is it's going to reduce the charge on oxygen. The charge on oxygen is going to be -1/2. Right? And so we have significant charge delocalization here. And so we have charge delocalization here, but one of the reasons why ethanol is such a poor acid, even though you expect it to be decent, yeah, yes, it's a little less polar, but still, it's the next best acid. But even though it's the next best acid, it's still very unreactive. It's very unreactive because of this. Can I draw resonance forms for this? No. No resonance forms for this. And so what we have is delocalized charge, localized charge. This charge is sitting in what orbital?
sp3.
sp3. So we got an sp3, it's stopped. We have 3 sp3 orbitals, three lone pairs, and 1 sp3 orbital bonding. The sp3 sigma bond. Yeah. This is localized. What else has localized charge like this? So this is electron rich. You got to remember that. This is electron rich in what was the oxidation state?
-1.
-1. Okay, not only do we have localized charge here, we have an electron pushing or electron withdrawing group attached to that. We have an electron pushing group, which is going to make that even more negative, making this even more basic. I mean, let's compare that to something like this. Hydroxide. This is a little bit tricky one, because what's the oxidation state on this hydrogen here? That's +1. You think, oh, okay, +1 should be electron withdrawing, but hydrogen's happy at +1. So it's not much, let's say, electron withdrawal, perhaps. It's hard to get a gauge. But you would expect this to be a strong base or a weak base. This is a strong base. And this is what makes ethanol so unreactive, even though it's got decent polarity. Decent polarity, but the product is quite unstable. It's pretty strong base. All right, so this is what would you call the reverse of the inductive effect? We'll let Alex name it.
Oh, I can name it?
Yeah.
The opposite of the inductive.
Yeah, what's the opposite of inductive effect?
Convection effect.
Convection effect?
If we're using induction, it might not convection.
Convection because it goes back around. Something comes back.
Exactly. We're talking about heat transfer.
All right, the convection. I'll call it the pushing effect. Here's the pushing effect for me. Over here, this would be the inductive effect here, because this carbon is what oxidation state?
-3. +3.
Yeah, this carbon here is +3, which means that the charge is actually less than -1/2. It's actually less than -1/2 because we have an electron withdrawing effect here. And so we look at that too. So when we do charge localization, delocalization, we look at the inductive and the pushing or the convection effect, and we look at withdrawing effects there, as well as resonance. And so we have to consider the product. The product's important, especially in a case like this, because acetic acid was how many times more acidic than ethanol? So let's go back and take a look at the Kas and the pKas that we have for this. When we look at the numbers, yeah, right? This is 10 to the negative 5. This is 10 to the negative 16. That's 11 orders of magnitude. So that means that ethanol is 1 order of magnitude would be 100 billion times weaker. So if ethanol is 100 billion times weaker, it's 100 billion times less polar. So if you only argue based on polarity, it's too weak of an argument. You know, we need to look at more factors because there's just a huge discrepancy. I mean, if it were a minor difference, then yeah, sure, polarity is probably it. You know, but with such an enormous difference, then you can't just say it's more polar. Inductive effect, it's not enough. And so here they show delocalization, localization. Okay, if we go to chloroacetic acid here and compare it to acetic acid, it's 10 to the minus 5. This is 10 to the minus 3. So it looks like chloroacetic acid is about 100 times stronger than acetic acid. So what would the reasoning be for that? Inductive effect. So let's take a look at the inductive effect here. One thing about organic chemists, they don't write lone pairs. And if you were in an organic chemistry class, there'd be no lone pairs in the chlorine, and there'd be no lone pairs in the oxygen. This is half and half. I don't know. Maybe Petrucci's trying to bridge between general, in which you're going to write all the lone pairs, and organic. But this Lewis structure is screwed up, because it should be one way or the other. Or either leave them all off, or put them all on.
Do you know why they do that, Professor?
Why do the organic chemists do that?
Yeah.
Because
It takes so much time for it.
number one, it takes too much time to write all the dots. Number two, somebody can look at the structure and immediately see it. You know, like for this, organic chemists, when they look at this structure, you can immediately see it. Can you see it? This is cyclohexane. How many hydrogens are on each carbon? 2, and how many double bonds are there? And so when you see a structure without lone pairs, then you know you've seen it so many times you can see it. The problem is that when people are starting out, they don't know, and so you have to make sure you do it. And then once you can visualize this, like if there were no lone pairs here, I could easily see how many lone pairs there are. This is typically the way it's written. I'd see how many lone pairs there are. I mean, just looking at it, I can see how many lone pairs there are. You know, and so when I visualize this in my mind, I already see the lone pairs there. You know, and so this is just and eventually, organic chemists don't even write it like this. Do you know how acetic acid is written? This is acetic acid. It's easier. Chloroacetic acid. Chloroacetic acid. Dichloroacetic acid, trichloroacetic acid. Trichloroacetic acid is an interesting one here.
Isn't that mistake?
No, because of its strength. You memorized the 7 common strong acids, but did you know there are more than 7? This one you can buy in the supermarket, trichloroacetic acid. I think they use this as a wart remover. But it's a strong acid. This is a strong acid. Chloroacetic acid is still a weak acid. It's a weak acid, but it's 100 times stronger than acetic acid. Trichloroacetic acid is such a strong acid because of the inductive effect. So there are two ways of visualizing that. Okay, so we already know what this card is here. This card is a +3, right? But then we look at the next carbon over. Okay, this one is going to be a plus what?
Right. Not +3.
This one's a +3. This one's a +3. This one is a
Zero. Plus. Minus.
minus. So we can already see here the difference in the next carbon over. You see, one is this electron pusher or electron withdrawer? Well, I think that's slight pusher, -1, but it's going to be a withdrawal compared to -3, which is on acetic acid. And so it's all relative. But compare these two, there's a big difference. That's one way. This is doing oxidation states. So we're going to see a much larger inductive effect here, much smaller. In fact, if this is rich, then it's going to be it's going to be the opposite. It's going to be a pusher rather than a puller. Correct? So this is going to be a much stronger acid than this. However, what we typically do is we typically do this like this. We typically use the arrows. Using the arrows, we just go in line with this. So we have this oxygen here. That's terminal oxygen pulling electron density. We have this chlorine here pulling electron density, and that's going to suck a lot of electron density from hydrogen. We have that. Versus acetic acid. And so what that's going to do is it's going to make the delta H on hydrogen much bigger. And so number one, it's more polar. Number two, what can you say about the conjugate base?
More stable.
It should be more stable than acetate. So chloroacetate is going to be chloroacetate. Is more stable than acetate. Why?
Because the negative charge is more delocalized.
It's more delocalized because we have both resonance delocalization and inductive effect. And
Is
so
the chlorine the terminal negative atom as well?
the terminal electronegative, in this case, it would be because we have one more resonance form for this, and then we look at the hybrid. When we look at the hybrid's going to look like this. Hybrid looks like this. And so the inductive effect is going to be, we don't call this a terminal because both of these are terminal. So there's no distinction there. But we're looking at here, we're looking at this -1/2, which is the average charge on each oxygen. And then we're looking at this. Rather than having a methyl group here, methyl group is an electron pushing group or electron withdrawing group, a methyl.
Withdrawn. It's negative.
If it's negative,
Electron rich is a withdrawn.
electron rich withdrawing, electron, okay, maybe I should phrase it wrong. Is it an electron convection group or electron withdrawing group? Methyl.
It's still electron withdrawn.
So in organic chemistry, you would quickly see the group, and then you could easily analyze it. Is that electron rich or electron poor?
Electron rich.
It's electron rich.
Which makes it
So it wants more electron density sucked towards it. It's going to withdraw electron density from other groups, whatever it's attached to. Is that correct?
That's what withdrawing gives it, right?
Oh, it has extra electrons, so it's like, oh, take my electrons.
If it's rich, it can spread the wealth of electron density
To atoms?
to other atoms, right? If it's electron poor, it's going to want to take electron density from other atoms.
If it's too much electron rich, then it might give some of this electron to the other.
Yeah, right. So this is very electron rich. Methyl groups are electron rich, right?
But more electrons than electrons.
It's a pusher. It's a pusher. It's got,
Write down something real fast.
yeah, write it down.
Switch around the names.
Yeah, switch around the names. Just flip them. So compared to a methyl group, this one will be more of a withdrawer or more of a pusher or what? What is it? So this is what we're talking about. We're looking at this part of acetate, the hybrid, the resonance delocalized structure. This is very common. You know, the, do you see that? The red, the pi bonds. That's what I'm trying to show. The orbitals. You see the orbitals. In our book, we have the orbitals, but I'm just going to skip. And I'm just surprised we don't have it. Pi bonding, p orbitals. Okay, I guess not. It's very common. Oh, here it is. But this is a hand drawing. Anyway, this one tweaked. This is not good. This is good. So we have orbital overlap. And so we compare that, we call these substituents. We compare the two substituent groups that are attached here. Which one's richer? Which one's poorer?
Yeah. C is richer.
Yeah, the methyl group's richer than the chloromethyl. I mean, methyl group is richer than the chloromethyl group. Oh yeah, that's one way of doing it. The other way of doing it is by oxidation state. This one's a -3. This is a -1. The formal charges are both the same, they're 0. And finally, the other way of doing it is by an induction effect. This one is a pusher group, so it's pushing it that way. This one's going to be a withdrawer group, even though it's -1. It's going to be a withdraw because it's terminal chlorine, which is electronegative atom there. And so it's going to be more withdrawing. I don't care about the accuracy here necessarily, but when we set up a chain for inductive, it's always going to be a chain of arrows pointed to that terminal atom. You're not going to flip this one the other way, even though you should, because this is -1 carbon, and this carbon is what? This is a +3 carbon. And so -1 carbon versus +3 carbon, which carbon is going to win? Win the tug of war for electron cloud density, +3. And so this arrow should really be pointed to the other direction, but we don't do that in the inductive effect. And so what this is showing is withdrawing more in that sense. And so, now don't worry about the arrow directions here. You know, I didn't write it here, but I did write it here. The arrow should be pointing towards this carbon because it's plus 3 carbon versus minus 1. They got in a total word. For sure the plus 3 should be. And so the inductive effect is you just ignore all those and you just draw a chain of arrows headed like ants to the terminal atom. Which one do you pick? Phosphoric acid or chloric acid? Chloric acid. And why? Is more electronegative. More electronegative. Which one's more electronegative? Chloric acid. I mean, what do you mean? You can't just say electronegative. Because electronegative refers to a specific atom. The hydrogen's more electronegative. In the chloric acid, well, they both have hydrogen. The hydrogen is more electronegative than the phosphorus. And so, what does that do? The only thing that makes the acid more stable. Well, what does that do in terms of bond strength, polarity, and stability of conjugate base? I see that answer a lot in tests and quizzes. It's more electronegative. That's all they know. Sometimes they get it wrong. Like sometimes I'll ask, which is a stronger base? Here, I'll draw the electrons. Which of them is a stronger base? And they'll pick this one. Why? Because it's more electronegative. Is that the reason this one's a stronger base? Well, it is more electronegative, that's correct. What's the reason? Is this one the stronger base or this one the stronger base? Bromic is the stronger base because it's further away, right, with the bond, making it easier to break the bond. Yeah, if it's further away, it would be easier to break. So the bond energy, this is the bond energy issue? Okay. It's not, we're not breaking this bond. I would say if it had an H, that would make the difference. It's more attractive. Well, basically, the test is with water. You know, which one is going to have an easier time plucking the hydrogen off water? And why? So bases follow a different set of criteria. What's the criteria for base?
Resonance to localization.
Well, what's the top priority for a base? No, we don't look at bond strength for bases.
Stability.
We don't look at stability initially for base. We look at negative charge density, negative charge. So this question might come up. Which one's a stronger base? Usually formal charge is everything in normal -2. Oxygen. And you know the common answer I get? Maybe from 10%. It's more electronegative. I see that answer all the time. I'm trying to. Yeah, it's smaller. That's what I like that answer better. It's smaller. Meaning its charge density is going to be more concentrated. I mean, it's a lot smaller. Therefore, it's going to be more reactive. Coulomb's law depends on charge. The more negative this is, the better fucking that hydrogen. This is less negative because it's more diluted, I guess, the charge over a bigger volume. And so they try to apply the exact same argument over here, and it fails. Do you see why it fails? So yeah, they say, okay, oxide versus sulfide, oxide's more electronegative, therefore it's going to be a stronger base. We get the answer right. Good. Then they go over here and they try to play the exact same argument. Chlorine versus bromine, chlorine is more electronegative, therefore this is going to be a stronger base. Is that right?
No.
No, it's not, but I see this all the time because I designed the question to test this. See if they're going to use the electronegativity argument. And so what's the reason why hypobromide is a stronger base than hypochlorite?
It's bigger, it has more surface area, more attachments for water to come in.
Because oxygen is able to hold more electrons from bromine than from chlorine.
We don't, this is a bigger atom, and it's going to have a longer bond, but we're trying to make a new bond. When this plucks off the hydrogen, we're going to make the conjugate acid, which is hypobromous acid. And when this plucks off a hydrogen, we're going to make the acid, hypochlorous acid. And so the bond that we're forming is with oxygen in this. Nothing's happening with this bond. It's not changing. If it's not changing, then not going to worry about it too much. But there is something that's related to size. There are a number of things that are related to the size. One is charge density. Well, properties from chapter 9. Related to size are things like reactivity, like electronegativity is related to size. The ionization energy is related to size. Electron affinity is related to size. Many things are related to size. And so, but on this particular case, it's just the inductive effect. That's all. Chlorine is going to have a larger inductive effect that is an electron withdrawing. Both of these are electron withdrawers, right? Which one is a greater electron withdrawer, chlorine or bromine? Well, chlorine. So since chlorine's a greater electron withdrawer, it's going to suck more of the negative charge. So this is going to be less than -1, and this is going to be a little less than -1. But this, so we're going to have more charge on this hypobromite than this. And so we have to frame it in those arguments. You don't want to start talking about, secondary bonds or tertiary bonds or those types of things. You want to just focus on what's most important, the charge density. What's more powerful, of a base, hydroxide or oxide?
Oxide.
Yeah, oxide. Higher charge. So for bases, we look for charge density. How do we lose charge density? We can lose charge density through inductive effect. We can lose charge density due to delocalization. Here. Going from -1 to -1/2. Or a combination of resonance delocalization and inductive. And so we have to be on the lookout for that. And so let's take a look at analyzing 1 and 2, phosphoric versus chloric acid. I think everybody said chloric acid stronger, and the reason was electronegativity. Okay, that could work. Let's take a look. So phosphorus is less electronegative, right? But this phosphorus is also bonded to more oxygen. Are oxygens electron withdrawers or electron pushers? Electron withdrawers. And so that's going to change phosphorus. A normal phosphorus is not normal phosphorus.
Average phosphorus either.
Because it has all these oxygens trying to take its electrons. This oxygen is in great distress. This phosphorus is in great distress. Too many oxygens, right, are trying to take. Not only that, what is the formal charge on phosphorus?
Formal charge? Positive.
Formal charge. The chlorine seems to be faring a little better because chlorine has its own pair of electrons. It doesn't have to share with anybody. And it doesn't have as many oxygens trying to take its electrons. So what's the formal charge on chlorine here?
Plus 2.
Plus 1, 2, 3, 4, 5, plus 2. It's pretty high, isn't that? Yeah, especially for chlorine. And so we would expect, even though this phosphorus has a greater inductive effect, do you see how this phosphorus has a greater inductive effect? There's another situation, and that is phosphoric acid versus phosphorus acid. So if we take a look at phosphorus acid,
Yeah, the oxygen?
You can force acid as well.
Yeah, it is wrong.
You have an extra oxygen.
sometimes it's hard to see things.
For me. Don't worry, I still sometimes.
Even though I look at it over and over. I guess it's too much of those imaginary visualizations of electron pairs and that kind of stuff. It's all mixed up sometimes in the mind. But anyway, the typical argument for this is phosphorus acid versus phosphoric acid, greater inductive effect. So here we only have 3 oxygens pulling. Over here we're going to have 4 oxygens pulling. The terminal ones, usually we do the terminal ones, Here there are no terminal ones. And so the inductive effect is like this. You see, we got these 4 oxygens pulling, but when we do the inductive effect using arrows, all the arrows point to the terminal oxygen. So doing the inductive effect, we have all the arrows going towards that oxygen. And so this is typically, the purple arrows are typically the way you draw inductive effect using dipoles like this. Here we have no terminal oxygen, and so therefore we don't have that effect. But anyway, phosphoric acid is a stronger acid. And then we could also look at the product stability too. But this is okay. I mean, you could have argued this, yeah, chlorine's more electronegative, that would probably work because it's going to be here. But not only that, it's got a +2 formal charge, making it even more electronegative. The book, I think, argued this one has 2 terminal oxygens, that one has 1 terminal oxygen. So let's see what the book says. Phosphoric acid has 4 oxygen atoms to 3 in HCl3, but it is the number of terminal oxygen atoms that we must consider. So when we do the inductive effect, we always go to the terminal oxygen. So this is why I showed the purple arrows here, disregarding the dipole on dipoles. So the inductive effect is without the terminal. And this is why I say there's no inductive effect here, because there's no terminal oxygen. So their argument is that HClO3 has 2 terminal oxygens, but H3PO4 only has 1. Also, the chlorine atom, electronegative 3.0, is considerably more electronegative than the phosphorus atom, electronegative 2.1. These facts point to chloric acid as being the stronger of the 2 acids. It's like 100,000 times stronger. Okay, how about this one here? The second one's stronger?
Yes.
Yeah. That's correct. Yeah, these fall off pretty distant. So if we do this, if we're doing inductive effect, the closer the better. And so as far as that, but you know, here they actually in organic chemistry they have names for these carbons. So if we're looking at acetic acid here, do you know this first carbon off this on the substituent? They give it a name. You know what name they give that carbon? The alpha carbon. The second carbon, you know what they gave this? The beta. The beta. Which one's going to be more important? Alpha, beta. What's after beta? Charlie. Not Charlie. G. Gamma. Alpha, beta, gamma. And so we have names for these, so we can see, you know, what types of groups will have what types of effects on the structure. You know, alpha is going to be more important, of course, than the others. So this is like an alpha chloro versus a beta chloro. Alpha chloro is going to have a more significant impact on the inductive. We can also do oxidation states as well. The oxidation state on this carbon is
Would it be B+1? Or
well, 0 is right. It's 0. Oh. 2 from this, 1, 1, and none. So that's 4, 0. And so this is 0. How about this alpha carbon? What's the oxidation state on this alpha carbon? -2. Right. And so 0 versus -2, this one's a lot richer. Let's go to the beta carbon. What's the oxidation state on the beta carbon over here? -3. -1. So all these factors we look into and see, you know, how much of an electron pusher or how much of an electron withdrawer these are going to be for both acids. For acids, we want electron withdrawers to increase the strength. We want electron pushers to withdraw, to lower the strength. All right, now we're going to look at bases. Actually, I forgot to look at that. I think that was maybe caffeine. You know, there are a lot of drugs and that are bases.
Do you have a favorite professor?
Me?
Yeah.
Favorite drug?
That is base.
Yes. Oh, that's a base. Advil, maybe? My favorite? I don't know. Well, Advil is nothing for my leg right now. I'm hating it. Trying to increase the dose to 600 milligrams. I don't know if that's going to work. caffeine. But I know, I let me take that back. I'm on decaf now, so I don't like caffeine.
Isn't caffeine an acid?
I thought it was massive. Let me see. I thought that thing in your tattoo was caffeine, but I could be wrong. It's, well, whatever it is, it's an amine, and they're lost. Like, you know, meth. Meth is an amine, right? Oh, there's everyone's favorite. Hydroxychloroquine. Have you heard of hydroxychloroquine? Hydroxychloroquine. Let's take a look.
Oh, I think I know what caffeine is. Caffeine is a weak base.
Hydroxychloroquine. There are people who love it and people who hate it. And this has become very polarized, this drug. Yeah. It's a base. Hydroxychloroquine gets in your cell and changes the pH of your cell, intracellular fluid.
So it's a strong base, right?
No, it's a weak base. You don't want a strong base. A strong base would change it too much. You can't change the pH too much without causing too much damage. So it's a very, very mild base that changes the pH just a little bit. When it changes the pH, it changes how the proteins fold and it can denature. Have you heard of denature? Denature is screwing up the structure. Uh-huh.
That's the drug that people were saying to take for COVID-19, but it didn't work.
It worked with I think.
For a time?
And then there are people who are saying it didn't work. So there are conflicting studies. But conflicting studies means you can't say with 100% certainty that it doesn't work or 100% certainty that it works, you know. So if you get conflicting studies, you want more studies. Uh-huh.
Just mean caffeine is a weak base.
Yeah, right. Caffeine's a weak base. But we don't use caffeine to change the pH of your cells. Hydroxychloroquine was used to change the pH of the cells. It's used for many things. It was one of the repurposed drugs for COVID-19.
Oh, one of my
But it's an amine. Yeah. You see, when you have this INE, when you have that INE ending, you know what it tells me? Hydroxychloroquine, caffeine, methamphetamine. What else do we have? We have, there are lots of amines. And so amines are an important class of organic bases. And so if you want amine drugs, let's see if I have a favorite amine drug. Oh, Sudafed is good. I love Sudafed. You know what? The nasal decongestant. So I take this. Although you have to buy it, you know. It used to be over the counter, but now you have to get it behind the counter, and then you have to give them your driver's license, and you can't buy too much within a certain period of time.
One of my favorites is I don't know what it is, but it's Zyrtec. I went biology book and take that a day.
I don't know what Zyrtec is, but
I think it was on there. It's
Fluvoxamine. Maybe I need to take this. Treat obsessive compulsive disorder. Amphetamine. Treatment of attention deficit hyperactivity disorder. Esmolol. What is this? Beta blocker. I know a lot of people who take beta blockers. Parkinson's. Yeah, it's interesting, you know, all these organic. So we're going to take a look at some simple amines right now. But these structures are interesting. I mean, we'll take a look at base strength. And so what all amines have in common is this.
I found it. Antihistamine.
Oh, antihistamine? Well, I have allergies, so I take antihistamine. Sometimes hay fever. Okay. Amines traditionally, we have R. You know what R stands for?
Oh, really?
Rest.
I always thought it stood for the rest of the molecule, other stuff, the R group. R is typically going to be a carbon or hydrogen. Carbon and hydrogen, what's the electronegativity of carbon? What's the, no, hydrogen is 2.1. What's the electronegativity of carbon?
2.6.
2.6. 2.5 or 2.6. I always had to memorize it 2.5, but whatever. It's close. And nitrogen's electronegativity is nitrogen number 2 on the electronegativity scale. And so what this makes is it makes a good base. This is a good Lewis base. This is a good Lewis base because we have negative charge density. Nitrogen is going to win. And we have a lone pair. So this is a good base. It's not a great base, but it's a good base. So like ammonia. Ammonia is a good base. Now, did I talk about power functions? When we're comparing the Kas, those were written in scientific notation. But I was just comparing the exponential, 10 to the minus 5 versus 10 to the minus 8. 3 orders of magnitude, 3 powers. And so these are the powers. These are power functions in KB. So this would be like between 10 to the negative 4 and 10 to the negative 5. Okay? Between 4 and 5. And so it would be something times 10 to the negative 4, something times 10 to the negative 5. This is between 10 to the negative 7 and 10 to the negative 8. So this is like the Richter scale. And so when I look at the Richter scale, I see a 4 versus 7. A 4 versus 7 is 3 orders of magnitude, so it's 1,000 times. And so ammonia is 1,000 times stronger, the smaller the stronger, than bromamine. But that's not an R group. What's bromo? Bromo is what we call, not an R group, what do we call bromo? Bromo is called, well, what do we normally give? Bromine's a halogen. So what symbol do we normally use for halogens? Not H. This is something you might have seen a couple of times in the past. What symbol do we use?
A.
A we usually use for anions and generic anion, but if that anion is specifically a halogen, then we use a different symbol for that. And it is N. N? N is we use for nitrogen. We got to make sure we take one that's not on the periodic table.
Nice, but a lot of halogen just HA.
HA is any acid. But if we're talking about a halo acid, like HCl, HBr, HI, then we use this symbol. Not HA, but H.
Oh.
Let me just, X. X is, this is where X is a halo substituent or halogen substituent. This is not a good base. What's more electronegative typically? Well, nitrogen is the second most electronegative. But if you put a halogen on here, then it changes things. Let's say if X is fluorine, how does it change it? Electronegative. For example, if I put 3 fluorines on here, does it make the delta minus bigger or smaller on nitrogen? It'd be way smaller. In fact, it flips. Fluorine would be the delta minus, and nitrogen would be delta plus. Is that a good base? No. Not a good base. So in other words, we want more negative charge. The way, well, how would you explain this? You know, ammonia versus bromine. You would explain it based on what? The inductive effect, right? Bromine's going to suck network. Bromine's sucking electron density. Even though nitrogen's more electronated, but bromine's going to put up a fight. And therefore, we say it's an inductive effect, and we point the arrow in the opposite direction of what it really should be. But it's just showing the net effect, you know, that it's not going to be easy for nitrogen just to take the electron density. And so when we look at bases, amines, we look for what substituents are attached, what R groups are attached to it. You know, that's what we're looking at. So a methyl group is electron rich or electron poor? Sorry. Electron rich. Electron rich. Is it going to be more basic or less basic? More basic. And so let's take a look. 4 to 3, that's 10 times stronger. And so having an electron pusher group like methyl makes it 10 times stronger base because we're going to have more negative charge density on the nitrogen, which is what we want. How about a methyl group? A methyl group is also an electron pusher or electron withdrawer. It's an electron pusher. So this is, you know, we're looking at the second, you know, this is -3, this is a -1. But then we have this -3 here versus hydrogen +1. And so we look at the next group here, the rich carbon versus hydrogen, which is 4. And so this is going to be better, but is it significantly better? No. No. Because the, what's that? Carbon. Because the, most important is the alpha carbon, followed by the beta carbon. All right, now we have some funny stuff here. Phenylamine. This is called phenyl. These benzene groups are, in organic chemistry, are pretty big phenyl. This is phenylamine. Phenylamine is going to be weaker or stronger? Let's take a look. Okay, this is cyclohexylamine. This is cyclohexane, and so this is a cyclohexyl group. This is phenylamine. This is a phenyl substituent. This is a amine group here. Now, when we look at electron pushers, electron withdrawals, it gets a little bit more complicated with rings. Normally, a hydrocarbon ring, like cyclohexane here, is electron rich. This is also a hydrocarbon group, and it should be electron rich. But what do you notice about the strength there?
It's much weaker.
It's how many orders of magnitude? It's 1,000,000 times weaker. Wow, 1,000,000 times weaker. Why? And it has to do with this. You would think that this benzene group would be electron rich, it'd be electron donor, but it turns out this phenyl group is actually not electron rich, electron donor, it's actually electron withdrawer. Now, why would this be an electron withdrawer? When we look at the oxidation states, we can see it. What's the oxidation state of this carbon? Here. 1, 2, 3, 4. 0. What's the oxidation state of this carbon? Plus 1. Plus 1. There's not a huge difference, right? Do you think that accounts for 1,000,000 times difference in the? No, not 1,000,000 times difference. And so this is it. So what we can have is we can have some electron withdrawing into the ring. And the reason it withdraws into the ring is because that extra electron density can be spread out over the entire p orbitals. You know, when we look at the p orbitals in this, they're all overlapping. Did I show you the benzene already with the p orbitals and the pp pi bonds? I think so. Yeah. And so, or we could draw resonance structures. So remember, we want more negative charge on the nitrogen. But if the electron pairs can be resonance delocalized into the ring, then it's going to have less negative charge density on the nitrogen itself.
I actually have a question about PP pi bonds.
Yes.
So you had, was it earlier you had showed with the hybrid structure between the resonance forms of acetate. You had showed the PP pi bond between both oxygen and carbon. Does that form 3 for a PPP pi bond, or is that just 2 separate PP?
No, it's just spreading out.
Okay.
It's just room to spread out. That's what you should. It's not the number of bonds, it's just spread out.
Okay, so it's just a spread out.
Yeah. Okay. The same thing here. This is showing it localized, but delocalized by resonance. The other way we could just show it is just spreading out over the PP pi bond orbital network. Now, these aren't equivalent resonance forms, you know, because of when you look at the formal charges, these are less stable, but they're contributors, and so that's going to decrease the charge a little. And so that's what creates. So benzene rings like this, we call these aromatic substituents, can be electron withdrawers. So that's going to have an interesting impact. I asked you to do cyclohexanol, right, versus phenol. Is that correct? You guys, did I draw this on the board? Actually, I don't need to draw it on the board. Let's do it over here.
What's the difference between cyclosine and metacyclosine? Value today is cyclosine.
Cyclosine
Metacyclosine.
and metacyclosine.
I don't know how you spell sorry, cyclohexyl.
Hexylamine?
Hexyl, yeah.
Hexylamine?
Yeah.
All right.
What is the meta prefix?
I'll talk about that in just a second. So this is basically the reason why aniline, which is the common name for phenylamine, is so much weaker is because we have resonance delocalization or delocalization of the lone pair into the ring based on those resonance forms there. Let's take a look at this. These which one is going to be a stronger acid? There are two ways to answer this. One is by looking at electron pusher and electron withdrawer. So for an acid, which one is going to be the stronger acid? Cyclohexanol, or this is called phenol.
Phenol should be stronger.
Phenol should be stronger. And why is that? Because
Whether due to delocalization, it would have
we could re-resonance delocalize these in there. Or we look at the conjugate base. The conjugate bases are going to be quite a bit different. And so most of the argument goes by the conjugate base. If we look at the conjugate base of cyclohexanol, we come up with this. Can this charge be delocalized into the ring? No. So we just have two hydrogens. I'll define the hydrogens. There's no way we're going to delocalize that charge into the ring. Versus this. How many resonance structures can we draw from this? Can you draw them for me? Why don't you, we have a few minutes left. Why don't you draw the resonance forms for this for me? They aren't all going to be equivalent. This is the best. It's not 6. So draw it and then tell me. It's not 6.